The nearest star to the Sun is close enough to feel almost reachable. Its light, leaving tonight, would arrive at your eyes in a little over 4 years. That star is Proxima Centauri, a small red ember low in the southern sky, and it drifts through space beside 2 brighter suns in a system we call Alpha Centauri, the closest stellar neighbourhood we have. For a long time, any planets there stayed hidden in the glare. Then the James Webb Space Telescope turned toward the brightest of those 3 stars, a sun much like our own, and in a single image taken in August of 2024, it caught a faint point of warmth exactly where a giant planet could sit. In the 2 later looks, that point was gone. Tonight we sit with that speck and ask gently what it was. Look up on a clear night from the southern half of the world, and you can find a bright pair of stars low near the horizon in a constellation named Centaurus. One of them is not really a single star at all. It is our closest stellar neighbour, a system called Alpha Centauri, and it sits just over 4 light-years away. That distance sounds huge, and it is. Yet in the scale of the galaxy, it is the star next door. Light is the fastest thing there is, and even so, the light touching your eye from Alpha Centauri tonight left it more than 4 years ago. A child who was born when that light departed would be walking and talking by the time it arrives. 4 light-years is hard to feel, so let me give it a shape you can hold. If you shrank the Sun down to the size of a beach ball and set it on a table, the Earth would be a grain of sand about 100 paces away. On that same scale, Alpha Centauri would be another beach ball, and it would sit thousands of miles off on the far side of an ocean. Everything between is empty and dark. That emptiness is the ordinary condition of space. Stars are rare islands in a very wide sea. We care about this particular island for a simple reason. It is the nearest one. When we dream of ever reaching another star, or of studying another planetary system up close, Alpha Centauri is the first place we look, because it is the only place within anything like reach. And in the last 10 years, this nearby system has turned out to be far busier and stranger than anyone expected. The story we are following tonight begins here, with the nearest light in the sky, and it ends with a single faint point of warmth, caught by a telescope 1,000,000 miles above your head. Between those 2 things lies a puzzle. In one image, taken in the year 2024, the James Webb Space Telescope seemed to catch a giant planet sitting in a place where a giant planet has no easy business being. In 2 later images, that point of light was simply not there. We're going to walk the whole way to that speck slowly so that when we reach it, you understand exactly what was seen, why it was surprising, and why we still cannot be sure. To do that, we first have to meet the neighbourhood. Alpha Centauri is not one star but a family of them, moving together through space, bound by gravity across enormous distances. Some of those stars are much like our Sun. One of them is a small red ember that has become one of the most studied stars in the entire sky. Around that ember circle, worlds we have only recently learned to detect, worlds so light that finding them at all is a kind of miracle of patience. If this is the kind of slow, careful journey you enjoy, the sort that takes one real place in the sky and turns it over gently until it makes sense, then this is a good channel to follow, and you're welcome to subscribe and travel along. For now, hold on to the simplest fact. The nearest star to our Sun is close enough that its light reaches us in the span of a childhood. Everything else we learn tonight hangs from that thread of light and follows it home. Alpha Centauri looks like one star to the unaided eye, but a small telescope splits it into 2. Those 2 are called Alpha Centauri A and Alpha Centauri B. They are a matched pair, circling each other the way 2 dancers hold hands and turn. Alpha Centauri A is the larger and brighter of the 2. It is remarkably like our own Sun, a yellow star of nearly the same warmth and size, which is part of what makes this system so interesting. If you want to know whether Sun-like stars beyond our own can hold planets in the right place for life, Alpha Centauri A is the closest example you will ever get. Alpha Centauri B is a little smaller and cooler, an orange star, steady and long-lived. The two of them orbit their shared centre of gravity once every 80 years or so. During that slow waltz, the gap between them changes. At their closest, they come within about 11 times the distance from the Earth to the Sun. At their widest, they swing out to around 35 times that distance. To picture it, imagine the Sun and drifting somewhere out past Saturn, a second sun, orange and patient, always there in the sky. Then there is the third member of the family, and it keeps its distance. Its name is Proxima Centauri. The word Proxima means nearest, and it earns the name because of all three stars. It is the one that happens to lie closest to us right now. Proxima sits far out from the bright pair, at a distance of something like 13,000 times the Earth-Sun distance. It is so far from Alpha Centauri A and B that a single loop around them may take it more than 500,000 years. For most of human history, we did not even know these three stars were connected. They simply looked like separate points of light. Astronomers still debate the fine details of how tightly Proxima is bound to the other two, but the evidence points to a real family, drifting through the galaxy together. When you look toward that bright spot in Centaurus, you are looking at all three at once, blurred into a single glow by distance. This arrangement matters for our story in a very practical way. Two bright stars sitting close together in the sky are a nightmare for a planet hunter. When you try to block the light of one to search for faint planets beside it, the other one is still there, glaring into your instrument from nearby. It's like trying to spot a firefly next to one stadium floodlight, while a second floodlight shines from just off to the side. That difficulty shaped every attempt to find planets around Alpha Centauri A and B, and it explains why those two stars stayed empty on our maps for so long, even as the small red ember beside them gave up its secrets. So the system holds three suns. Two are bright and close and hard to study. One is faint and far and, as it turns out, generous with what it has revealed. Proxima Centauri is where the discoveries began, and it is where we go next, because to understand the strange speck near this system, you first have to understand the small red star that shares its name. Proxima Centauri is a red dwarf, and red dwarfs are the most common kind of star in the galaxy. They are small, cool, and dim. Proxima is a fine example. It holds only about an eighth of the Sun's mass, and its true diameter is roughly a seventh of the Sun's, which makes it not much larger across than the planet Jupiter. Its surface glows at a lower temperature than the Sun's, so its light leans deep into the red. If you could stand at a safe distance and look at it directly, it would burn a dull, ember-like orange, more like the coals at the bottom of a fire than the white blaze of our own star. Because it is so faint, you cannot see Proxima Centauri with your eyes alone, even though it is the closest star to the Sun. You need a telescope. This is a strange fact worth sitting with. The nearest star to us is invisible to the naked eye. It gives off so little light that its faint glow is simply swallowed by distance. Astronomers place Proxima at a little over 4 light-years away, closer to us than either Alpha Centauri A or Alpha Centauri B by a small margin. They also estimate its age at around 4 to 5 billion years, which is roughly the age of our own Sun. But unlike the Sun, a red dwarf like Proxima ages very slowly. It burns its fuel at such a gentle rate that it can keep shining for trillions of years, far longer than the universe has yet existed. Proxima Centauri is, in a sense, only just getting started. There is one detail about Proxima that makes it both fascinating and dangerous. It is a flare star. Every so often, magnetic energy stored in the star's outer layers snaps loose all at once, and the star briefly brightens in a violent burst. In March of 2017, Proxima let off a superflare so strong that, for a few seconds, the star grew many times brighter than normal. A burst like that floods everything nearby with radiation and streams of charged particles. For any planet orbiting close to Proxima, those flares are a serious problem, because they can strip away an atmosphere over time or scour a planet's surface with harmful energy. That matters, because Proxima Centauri, faint as it is, holds planets. Since a red dwarf gives off so little warmth, the region where a planet could be mild enough for liquid water sits very close to the star. A world in that gentle zone would orbit near the fire, close enough to feel each flare, so the same nearness that makes Proxima's planets easy to warm also makes them easy to harm. Understanding this small red star is the key to everything that follows. Its faintness is why its planets were found first, because a dim star does not drown out the subtle signals of a world tugging on it. Its flares are why we worry about whether those worlds could ever be gentle places, and its position as the nearest star in the nearest system is why every planet found around it, and every faint speck found near its bright siblings, matters so much to us. Proxima is small, quiet, and close. That combination has made it one of the most closely watched stars in the entire sky. There is a longing behind all of this, and it is worth naming plainly. Since we first understood that the points of light in the night sky are other suns, people have wondered whether we could ever go to one. Alpha Centauri is the answer to the question, if we ever could, which one would we try first? It is the closest, and so it has become the natural target for every serious dream of reaching another star. The trouble is the sheer size of the gap. Our fastest spacecraft so far, the ones that have left the solar system, are crawling by the standards of interstellar travel. If one of them were pointed at Alpha Centauri, it would take tens of thousands of years to arrive. A journey begun at the dawn of human farming would still be underway today. So reaching Alpha Centauri with the rockets we know is not really travel at all. It is a message in a bottle thrown across an ocean that takes longer to cross than civilizations last. This is why the nearest system draws such careful attention from the ground. If we cannot easily go, then the next best thing is to look, and to look as closely as physics allows. And Alpha Centauri offers something no other system can. Because it is so near, any planet we find there appears larger and better separated from its star than the same planet would around a more distant sun. Nearness turns a hopeless smear into something we might actually resolve. The closest system is not only the one we most want to reach, it is also the one we can study in the most detail. That is the real prize. Not a photograph for its own sake, but the chance to learn what a nearby planetary system is truly made of. We want to know whether sun-like stars beyond our own routinely hold worlds in the mild zone where water can pool. We want to know whether those worlds have air and weather and perhaps the faint chemical fingerprints that life leaves behind. Alpha Centauri is the one place where those questions might be answered clearly rather than guessed at from afar. There have even been serious proposals to send something there, not a heavy ship, but a swarm of tiny probes no larger than a chip, pushed to a fraction of the speed of light by powerful lasers. We will come back to that idea near the end of our journey, because it is a genuine plan that people are working on now, not a fantasy. For the moment, hold on to the shape of the wish. We want to know our nearest neighbours the way you might want to know who lives in the house across the valley, whose lights you can see but whose faces you have never met. Everything else in this story flows from that wish. The patient searches, the clever instruments, the strange speck of light caught by a space telescope. All of it is the reach of people trying to see across an ocean of dark. The distance will not let us walk over and knock on the door, so we have learned instead to read the faint signs that leak across the gap. The first of those signs came not from the bright pair, but from the small red ember. It was the discovery of a planet, and it changed how the whole world looked at the star next door. In August of 2016, a team of astronomers announced that they had found a planet orbiting Proxima Centauri. They called it Proxima Centauri B, or Proxima B for short. It was, and still is, the closest known planet beyond our own solar system. Overnight, the nearest star stopped being an empty point of light and became a place with a world. The discovery came out of a campaign with a lovely name, the Pale Red Dot. The name is a nod to the famous image of Earth as a pale blue dot, and it captures the hope behind the work to find a small world around a small red star. The team was led by the astronomer Guillaume Anglada Escudé, and they watched Proxima Centauri night after night from an observatory in the mountains of Chile, run by the European Southern Observatory. Their main tool was an instrument called HARPS, a spectrograph attached to a telescope with a mirror a little over 3.5 meters across, at a site called La Silla. What they were looking for was not the planet itself. Proxima b is far too small and faint to see next to its star. Instead, they were looking for the star's response to the planet. A planet and its star both pull on each other. The star is far heavier, so it barely moves, but it does move, tracing a tiny circle as the planet swings around it. From our vantage point, that small motion shows up as the star drifting a hair toward us, and then a hair away, over and over, in step with the planet's orbit. The size of that drift for Proxima b is astonishing in its smallness. The star's velocity toward and away from us changes by only about 2 meters per second. That is roughly the speed of a person walking at an easy pace. Across 4 light years, the team measured the star quickening and slowing by no more than a stroll, and from that whisper of motion, they read out the presence of a hidden world. Proxima b turned out to be a rocky planet, a little heavier than Earth, with a minimum mass of around 1 1/10 times our own. It circles Proxima Centauri once every 11 days, which means its year is shorter than 2 of our weeks. It orbits very close in, at only about a 20th of the Earth-Sun distance. Around our Sun, that would be a scorched and hopeless place. But Proxima is so cool and dim that this close orbit lands the planet squarely in the mild zone, where the warmth is gentle enough that liquid water could, in principle, survive on the surface. That is what made the discovery electric. Here was an Earth-sized world in the temperate band around the very nearest star. It was the best possible target for every future dream of studying another Earth. There are honest doubts, and they deserve saying plainly. Because Proxima is a flare star, the planet is battered by radiation far stronger than anything Earth endures, which may have stripped away any atmosphere long ago. And some later studies have argued that part of the wobble might come from the star's own restless surface rather than a planet. The signal has held up well overall, but the world it points to remains a place we know mostly by inference. We know Proxima b exists chiefly because a star 4 light-years away sways by the speed of a walk. It is worth slowing down on how that trick actually works, because the same idea runs through much of this story. The method is called radial velocity, and once you see it clearly, a great deal of modern planet hunting falls into place. Start with the picture of a star sitting perfectly still while a planet orbits around it. That picture is not quite true. Gravity always pulls both ways. The star tugs the planet into its orbit, and the planet tugs back on the star. Because the star is far more massive, it hardly budges, but it does budge. Both the star and the planet actually orbit a shared balance point between them. The planet swings around in a wide circle, and the star traces its own tiny circle in response, like a large person and a small child spinning while holding hands. The adult barely shifts their feet, yet they still lean and turn. Now add our point of view. We watch the star from far away, roughly edge on to that little circle it is tracing. So as the star moves through its small loop, part of the time it drifts slightly toward us, and part of the time it drifts slightly away. Toward, then away, then toward again, in perfect rhythm with the planet's orbit. Here is the elegant part. Light itself carries a record of that motion. When a source of light moves toward you, its waves get squeezed a little shorter, shifting toward the blue end of the spectrum. When it moves away, the waves stretch a little longer, shifting toward the red. You may have heard the same effect in sound, in the way a passing siren drops in pitch as the vehicle goes by. Light does the same thing, quietly, and an instrument sensitive enough can measure it. A spectrograph is that instrument. It spreads a star's light out into its colours, the way a prism spreads sunlight into a rainbow, but in fine detail. Threaded through that spread of colour are thousands of narrow dark lines, fingerprints left by the elements in the star's outer layers. Those lines sit at known places. As the star drifts toward us and away, all of those lines shift together, ever so slightly, toward blue and then toward red. By tracking that shift with great care, astronomers can measure how fast the star is moving toward or away from us, down to a fraction of a walking pace. The rhythm of the shift tells you the length of the planet's year. The size of the shift tells you how hard the planet is pulling, which reveals its mass. There is one honest limit built into the method. It measures only the motion along our line of sight, so it usually gives a minimum mass rather than an exact one, because we do not always know the tilt of the orbit. If the orbit is tilted so we see it more face-on, the true mass could be larger than the minimum we measure. Still, for small close-in worlds, radial velocity has been the great workhorse. It does not show you the planet. It shows you the star flinching under the planet's pull. For Proxima Centauri, that flinch was about the speed of a walk. For the next world we will meet, and then the one after that, the flinch grows fainter still, until we reach a planet so light that the star it circles barely seems to move at all. Proxima Centauri B was not the end of the story around that small red star. As astronomers kept watching, hints of other planets began to surface in the data, and the second of them is a genuine puzzle to this day. It is called Proxima Centauri C, where Proxima B hugs its star, orbiting once every 11 days. Proxima C keeps a much wider path. It appears to circle the star only once every 5.5 years or so, at a distance more than 100 times greater than Proxima B's orbit. That places it far out in the cold, well beyond the mild zone. If Proxima B is a warm inner world, Proxima C is a distant frozen one, with an estimated temperature far below the freezing point of everything familiar. Proxima C is also much heavier than Proxima B. The estimates put it at around 7 times the mass of Earth, which makes it a super-Earth, or perhaps a small version of a gas-rich world like Neptune. Its presence was first suggested by a long, slow signal in the star's radial velocity, a gentle multi-year rise and fall layered underneath the faster 11-day rhythm of Proxima B. Later, astronomers went back through old images taken by the Hubble Space Telescope and found what may be the planet itself, tucked in the archived data from years before anyone knew to look. That kind of confirmation, finding a planet in pictures taken long ago, is a quiet triumph of careful work. But here the puzzle deepens. When astronomers examined the possible glimpse of Proxima C, it looked brighter than a planet of its size and coldness had any right to be. A world that, far from a faint red star, should be dim, reflecting only a thin trickle of light. Instead, the object appeared to shine more strongly than expected. One idea put forward to explain it is that Proxima C might be surrounded by a broad system of rings, like a smaller cousin of Saturn, catching and scattering extra light across a wide disk. Another possibility is that the bright point is not the planet at all, but a distant background object that happened to line up. That uncertainty is why the status of Proxima C remains genuinely disputed. Some analyses support a real planet on that wide, slow orbit. Others find the evidence thinner and caution that the long signal could have other causes. It sits in that honest middle ground where the data allow a world but do not yet insist on one. There is something fitting in this. The nearest star, the one we can study better than any other, still holds a planet we're not sure about. Even at 4 light years, the closest possible distance, nature keeps a few cards face down. Proxima C may be a ringed super-Earth drifting in the deep cold at the edge of its system. It may be a subtle pattern in the numbers, or a stranger far behind the star. We do not yet know, and the people studying it are careful to say so. We will meet that same tension again, in a sharper form, when we reach the speck of light that Webb caught near this system. A single, bright point, an exciting possibility, and an honest string of doubts about whether it is truly there. Proxima C is a gentle first taste of that problem. The third planet around Proxima, by contrast, is the opposite kind of story, a discovery so delicate it stands as a landmark in the whole craft of finding worlds. The third world around Proxima Centauri is the lightest of the 3, and finding it at all is one of the most delicate measurements ever made in this field. It is called Proxima Centauri D, and it was announced as a candidate in February of 2022. Proxima D is tiny. Its mass is only about a quarter of the Earth's, which places it somewhere between the mass of Mars and something even smaller. That makes it one of the lightest planets ever detected by watching a star's motion. It orbits very close to Proxima Centauri, completing a lap in just over 5 days, on a path even tighter than Proxima B's. At that distance, sitting just inside the warm inner edge of the system, it is likely too hot to be gentle, though its small size and close orbit leave much still uncertain. To understand why this detection is such an achievement, return to the idea of the star's wobble. For Proxima B, the star swayed toward and away from us at about the speed of a walk, roughly 2 meters per second. For Proxima D, the sway is far smaller. The planet is so light that it pulls the star back and forth at only about 40 centimeters per second. That is slower than a gentle stroll. It is closer to the pace of a slow crawl, or a leaf drifting down. Across more than 4 light-years of empty space, astronomers measured a star nudging itself back and forth at the speed of a baby crawling, and from that whisper drew out a planet. The instrument that made this possible is called espresso, a spectrograph even more precise than the HARPS device that found Proxima B. It is mounted on the Very Large Telescope in Chile, a set of enormous mirrors run by the European Southern Observatory. Espresso was built specifically to chase these faint signals, the tug of small rocky worlds like our own, and Proxima D was one of its early triumphs. The work was led by astronomer Joan Faria and his colleagues, who had to separate the planet's tiny signal from the natural jitter of the star itself. For a while, Proxima D remained a candidate, a strong hint awaiting firmer proof. Then, in work published in 2025, a newer instrument called NIRPS confirmed the signal independently. NIRPS looks in infrared light and works alongside the older detectors, and its agreement gave astronomers real confidence that Proxima D is a genuine world and not a trick of the star's restlessness. A planet a quarter the mass of Earth at the nearest star, confirmed by catching a star's crawl speed sway. It is a quiet marvel of patience and precision. Step back and take in the whole small system. Around Proxima Centauri we now count 3 planets, in one form or another. There is Proxima D, a featherweight world hugging the star on a 5-day orbit. There is Proxima B, a rocky, Earth-sized world in the mild zone, the closest possible target in our search for another habitable place. And there is Proxima C, a distant, disputed super-Earth in the deep cold, perhaps wearing rings. For a faint red ember most people cannot even see, Proxima has proven remarkably rich. Yet all 3 of these worlds were found the same way, by the star's motion, not by their own light. Around the bright siblings, Alpha Centauri A and B, that same method kept coming up empty. To understand why, and to understand why a giant planet there would be such a surprise, we have to turn to the trouble those 2 bright stars cause. Alpha Centauri. A and Alpha Centauri B are the bright, sun-like heart of the system, and for a long time they were also its great frustration. Proxima, faint and alone in its corner, gave up 3 planets. The 2 bright stars gave up almost nothing. To see why, you have to appreciate 2 separate problems they create, one about where planets can survive and one about how hard they are to see. The first problem is gravity. Alpha Centauri A and B orbit close together, swinging between about 11 and 35 times the Earth's sun distance from each other. A second heavy star that near does not sit quietly in the background. Its gravity reaches into the space around each star and stirs it. A planet trying to hold a stable orbit around Alpha Centauri A has to contend with regular tugs from Alpha Centauri B passing by. Out beyond a certain distance from each star, those tugs grow strong enough to fling a planet loose or scramble its path over time. so there is only a limited inner region around each star where an orbit can remain steady for billions of years. The good news is that the mild zone, the band where a planet could hold liquid water, sits inside that stable region for Alpha Centauri A. In principle, a temperate world could survive there. The harder question has always been whether large planets could form in the first place in such a stirred-up setting. When two stars share a birthplace, the disk of gas and dust that makes planets is truncated and disturbed by the companion. Many models suggested that building a big planet, a true giant, in the habitable zone of a star like Alpha Centauri A would be difficult. Small rocky worlds seemed more likely than a Saturn or a Jupiter. That expectation is exactly what makes the later speck so striking, and we will come to it. The second problem is glare, and it is brutally practical. When you try to find a planet by its own faint light, the enemy is always the star's brightness. A star can outshine a planet beside it by a factor of billions. Blocking that light is hard enough with one star. With Alpha Centauri, there are two bright stars sitting close together in the sky at once. If you mask the light of Alpha Centauri A to hunt for planets around it, Alpha Centauri B is still blazing away nearby, spilling stray light across your instrument from just off to the side. It is like trying to photograph a candle held beside one searchlight, while a second searchlight shines from the next hill over. This double trouble is why the radial velocity method, so successful at Proxima, struggled at the bright pair. The star's own surfaces are active and noisy, and their light is harder to pin down precisely when two of them crowd the field. For years, sensitive searches around Alpha Centauri A and B ruled out large, close-in planets, but could not confirm anything in the mild zone. The nearest Sun-like star had no known worlds, not because none could be there, but because we could not yet see them. So the system split into two moods. Around faint, lonely Proxima, discovery after discovery. Around bright, crowded Alpha Centauri A and B, a stubborn blank. To break that blank, astronomers needed a different approach. Instead of reading the star's motion, they would try to catch a planet's own glow directly. And to know where such a planet might be gentle enough to look for, they first had to define the one region that matters most, the narrow band we call the habitable zone. The habitable zone is one of those ideas that sounds simple and hides real subtlety. In plain terms, it is the range of distances from a star where a planet could hold liquid water on its surface. Too close, and any water boils away into vapour. Too far, and it freezes solid. In between lies a band where, with the right conditions, water can stay liquid, and liquid water is the one ingredient every living thing we know of requires. Because it depends on warmth, the location of that band moves with the star. A hot, bright star pushes its habitable zone far out, so a planet would need a wide orbit to sit in the mild region. A cool, faint star pulls the band in close. This is why Proxima Centauri, a dim red ember, has its gentle zone right next to the star, close enough that a planet there orbits in a matter of days. Alpha Centauri A, being much like our Sun, has its habitable zone at roughly the same distance ours sits, around the Earth-Sun distance give or take. A temperate planet there would take about a year to circle, much like Earth. Sitting in the habitable zone is only the first requirement, not a guarantee of anything. It is better to think of it as a place where the story could begin, not a promise that it did. Whether a planet in that band is actually mild depends on much more than distance. An atmosphere matters enormously. A thick blanket of gas can trap heat and warm a world that would otherwise freeze, or it can smother a world in a runaway greenhouse until the surface roasts. Our own neighbours show both extremes. Venus and Mars both brush the edges of the Sun's habitable zone, yet one is a furnace wrapped in crushing clouds, and the other is a frozen desert with barely any air. For a planet around Alpha Centauri A, the habitable zone offers a tantalizing possibility. Here is a star nearly identical to our own, at the closest reach in the whole sky. If a world sat in its mild band, it would be the best chance we could ever have of studying a temperate planet around a true Sun-like star, near enough to examine in real detail. That is the dream that kept astronomers pushing at the hard problem of the bright pair. Not just any planet, but a planet in the right place, around the right kind of star, close enough to know well. There is a quieter reason the habitable zone matters for our story, and it has to do with warmth as a signal. A planet in or near that band is warmed to a moderate temperature, and everything warm gives off heat as infrared light, the same invisible glow your own body radiates in the dark. A planet's warmth is faint, but it is real, and it shines out in wavelengths our eyes cannot see. If you build an instrument tuned to that heat, a warm planet stops being invisible and becomes a small, steady beacon. That insight is the bridge to the next part of the search. To find a planet by its own light around Alpha Centauri A, astronomers would not look for reflected sunlight in ordinary colours, where the star's glare is overwhelming. They would look instead for the planet's own heat, in the infrared, where a warm world can shine against the dark. But choosing to hunt for a planet directly, by its glow rather than by the star's wobble, is a very different kind of task, and it is worth understanding why that choice was made. There are two broad ways to find a planet around another star, and it helps to see clearly how they differ, because the shift from one to the other is what finally cracked open the bright pair of Alpha Centauri. The first way is the one we have followed so far. It is indirect. You never see the planet itself. Instead, you watch the star and notice the planet's effect on it. The radial velocity method reads the star's tiny sway. Another indirect method, called the transit method, watches for the small dip in a star's brightness when a planet crosses in front of it. Both are powerful, and together they have found the great majority of the planets we know. But both share a limit. They tell you a planet is there, and they can reveal its mass or size and its orbit. Yet they hand you very little of the planet as a thing in itself. You learn the shadow, not the object. The second way is direct. You try to actually capture the planet's own light, to separate its faint glow from the star's blaze, and record it as a distinct point. This is far harder because of the glare we keep returning to, but when it works, it opens doors the indirect methods cannot. Once you hold a planet's own light, you can spread it into a spectrum and read the fingerprints of the gases in its atmosphere. You can watch how its brightness changes as it turns. You can, in principle, begin to ask what kind of world it truly is and whether anything in its air hints at life. Direct light is the difference between knowing someone exists and finally seeing their face. For Alpha Centauri A, the direct path had a special appeal. The indirect methods had already struggled there, tangled up by the glare and noise of the two bright stars. And the whole reason to care about this system is its nearness, which is exactly the advantage direct imaging needs. The closer a system is, the wider the apparent gap between a planet and its star, and the easier it becomes to pry the 2 points of light apart. A planet that would be hopelessly merged with its star in a distant system might, at the nearest system of all, sit just far enough out to be caught on its own. There was also the matter of the kind of planet worth hunting. The indirect searches had grown sensitive enough to rule out large, close-in planets around Alpha Centauri A, the sort that would tug the star hard or block much of its light. What they could not rule out was a planet in the mild zone, farther from the star, pulling only gently. Such a world would barely move the star, but if it were large and warm enough, it might glow in the infrared brightly enough to be seen directly. The two methods were suited to different planets. Where the wobble went quiet, a direct look might still reveal something, so the strategy took shape. Point a powerful telescope at Alpha Centauri A, hide the star behind a mask, look in the infrared, where a warm planet's own heat can shine against the dark, and search the region around the star out in the mild zone for a faint point of light that the star's silenced glare no longer drowns. It is a beautiful plan on paper. The hard part is the glare, and beating it required a specific piece of engineering, a device that creates a small artificial eclipse inside the telescope itself. To catch a planet's own light, you first have to deal with the fact that its star is overwhelmingly brighter. The numbers are almost absurd. A star can outshine a planet next to it by a factor of many millions, sometimes billions, depending on the light you're looking at. Trying to see the planet is like standing in a dark field at night and trying to notice a firefly hovering just beside the beam of a lighthouse. The firefly is right there. You simply cannot see it, because the lighthouse floods your eyes. The tool built to solve this is called a coronagraph. The name comes from the sun's corona, its faint outer atmosphere, which is normally invisible because the sun's bright disk overwhelms it. Astronomers first built coronagraphs to study that faint corona by blocking the sun's disk, creating a small artificial eclipse inside the instrument. The same idea, refined and made exquisitely precise, is now used to hunt for planets around other stars. In its simplest form, a coronagraph is a tiny mask placed inside the telescope, exactly where the star's light comes to a focus. The mask blocks the direct light of the star, casting a small shadow while letting the surrounding sky through. With the star's glare suppressed, faint objects near it, objects that were there all along but hopelessly buried, can finally register. It is the artificial eclipse turned into a planet-finding machine. Hide the lighthouse behind a well-placed thumb, and the firefly beside it may swim into view. In practice, it is far more delicate than a thumb over a light. Starlight does not behave like a simple beam. It bends and ripples around the edges of any obstacle, spreading into faint rings and spikes that can hide a planet just as effectively as the raw glare did. So a real coronagraph is a careful system of masks and optics, shaped to catch not only the star's direct light, but also the ripples it throws off. Designing one that suppresses starlight cleanly, without also erasing the faint planet you're trying to find, is one of the hardest crafts in modern astronomy. There is one limit built into every coronagraph that matters greatly for our story. It is called the inner working angle. The mask has to be large enough to cover the star, and that means it also covers a small region of sky right around the star. Anything that sits too close to the star, inside that masked circle, is hidden along with the star itself. A planet is only catchable if it lies far enough out from the star to peek beyond the edge of the mask. Move the planet in too close, and it vanishes behind the very shield meant to reveal it. Hold on to that idea, because it becomes important later. A planet on a wide part of its orbit might sit safely outside the mask and be seen. The same planet months later, having swung closer to the star along its path, might slip inside the masked region and disappear from view, not because it is gone, but because it has moved behind the shield. A coronagraph does not just fight glare. It has a blind spot, a small circle of hidden sky wrapped tight around every star it studies. With a good enough coronagraph, and a telescope powerful enough to feed it, the dream of directly imaging a planet near Alpha Centauri A moves from impossible to merely very hard. The telescope that finally attempted it is the most powerful eye we have ever placed in space, and it was built in part to look for exactly this kind of faint warmth in the dark. The telescope at the centre of our story is the James Webb Space Telescope. It launched on the last day of December in 2021, rode a rocket up through the atmosphere, and then unfolded itself over the following weeks into a shape far too large to have flown up in one piece. It is the largest and most capable telescope ever sent beyond the Earth, and it was built by a long partnership of space agencies working across many years and many delays to get it right. Its most striking feature is its mirror, a great golden surface made of 18 six-sided segments fitted together into one honeycomb about 6.5 meters across. Gold is used because it reflects infrared light beautifully, and infrared is the kind of light Webb was made to gather. A mirror that size collects far more light than any earlier space telescope, which lets it see fainter and more distant things. To keep it working, the whole telescope had to be folded like origami to fit inside its rocket. then opened out in space in a sequence of careful steps, any one of which could have doomed the mission if it failed. It all worked. Webb does not orbit close to the Earth the way many telescopes do. It sits about 1 million miles out, at a special balance point in space where the pull of the Earth and the Sun combine to let it keep pace with our planet as we both travel around the Sun. This distant perch keeps it far from the warmth and light of the Earth, which matters enormously for an infrared telescope. To see faint heat from the cosmos, the instrument itself must be extremely cold, so that its own warmth does not swamp the signal. Webb carries a vast sun shield, roughly the size of a tennis court, that unfolds to block the Sun, the Earth and the Moon, keeping the telescope in permanent deep shade. Behind that shield, its instruments chill to hundreds of degrees below zero. Among Webb's 4 main instruments, one matters most for our story. It is called the mid-infrared instrument, known by the shorthand MIRI. As the name says, it works in the middle range of infrared light, the deeper heat wavelengths, further from visible light than the other instruments reach. MIRI is the coldest instrument on the telescope, chilled by its own dedicated cooler to just a few degrees above the lowest temperature there is, because catching that deep heat from faint objects requires the detector itself to be almost perfectly cold. Crucially for planet hunting, MIRI carries coronagraphs of its own, the artificial eclipse masks we spoke of, built right into the instrument. That combination is rare and precious. A very large, very cold mirror, gathering deep infrared heat, feeding a coronagraph that can hide a star. It is close to the ideal machine for the task of catching a warm planet's own glow next to a bright star. When astronomers wanted to search directly for a planet around Alpha Centauri A, MIRI was the natural choice. It could look in exactly the kind of light where a mild, warm world shines. It could mask the star's glare with its coronagraph, and it sat far above the atmosphere in the cold and dark, free of the interference that limits every telescope on the ground. To understand why that last advantage matters so much, and why the deep infrared is the right place to hunt, we need to look at the particular colour of light where warm planets give themselves away. Everything warm glows, not always in light your eyes can see, but it glows. Your own body, warm as it is, gives off a steady shine of infrared light in the dark, which is how a night vision camera can pick you out in a pitch-black room. The rule is simple. The temperature of a thing sets the kind of light it radiates. Very hot things, like the surface of a star, glow in visible light, bright enough to see. Cooler things, like a planet or a person or a warm rock at dusk, glow further down the spectrum in infrared, in wavelengths too long for the eye. This is the key to finding warm planets, and it changes the whole strategy. If you look for a planet in ordinary visible light, you're looking for sunlight it reflects, a feeble scattering of the star's own glare, hopelessly outmatched by the star beside it. But if you look in the infrared, you're looking for the planet's own heat, like the planet itself produces. In that deeper light, the contest between star and planet is far less lopsided. The star is still brighter, but the gap narrows, and a warm planet becomes a genuine source of its own rather than a dim reflection. The candidate that Webb would eventually study around Alpha Centauri A was expected to be warm, at a temperature of roughly 225 Kelvin. In everyday terms, that is bitterly cold, around 50 degrees below zero on the Celsius scale, colder than the harshest winter night on Earth. Yet it is warm enough to glow in the deep infrared, and the particular wavelength where such an object shines strongly is around 15 microns, well into the range that MIRI, the mid-infrared instrument, was built to catch. So astronomers tuned their search to that light, 15 micron infrared, the heat glow of a chilly but detectable world. Here is where Webb's high perch pays off in full. That deep infrared light, the very glow you most want to catch, is almost impossible to gather from the ground. The Earth's atmosphere is full of water vapour, and water vapour greedily absorbs infrared light before it can reach a telescope on the surface. Worse, the atmosphere itself is warm, and warm things glow in the infrared, so the very air above a ground telescope shines faintly in the same light you're trying to detect from a distant planet. Hunting deep infrared from the ground is like trying to hear a whisper in a room where the walls themselves are humming. Above the atmosphere, in the cold and the dark, those problems fall away. There is no water vapour to swallow the light, no warm air to glow and interfere. A cold telescope in deep space can gather the 15-micron heat of a faint world cleanly in a way no ground telescope ever could. This is the deepest reason Webb was the right tool. Not only was it large and equipped with a coronagraph, it sat in the one place where the exact light needed to find a warm planet could be gathered at all. So the pieces were in place. A warm planet glows in deep infrared. That glow peaks near 15 microns. MIRI catches that light, and Webb's cold, distant perch lets it catch that light without the interference that blinds telescopes on the ground. What remained was to point all of that at Alpha Centauri A and look. But Webb was not the first to try. A few years earlier, a telescope on the ground had caught the faintest possible hint of something, and that hint is where the real chase began. Before Webb ever turned toward Alpha Centauri A, astronomers had already gone looking there from the ground, and they had come away with a tantalizing, uncertain hint. That earlier effort set the stage for everything that followed, and it is worth knowing, because the later speck did not appear out of nowhere. Someone had glimpsed something first. The ground-based search was called NEAR, a name that fits its target well. It stands for New Earths in the Alpha Centauri region. The project was a special upgrade to an instrument on the Very Large Telescope in Chile, the same great observatory that later confirmed Proxima's featherweight planet. The instrument was a mid-infrared camera called VISIR, and for the NEAR campaign it was fitted with new optics designed to do exactly the hard thing we have been describing, to block the glare of a bright star and search for the faint heat of a planet beside it, from the ground, in the infrared. Searching in the mid-infrared from the ground is, as we saw, a brutal task, because of the atmosphere's own glow and its hunger for infrared light. NEAR pushed against those limits with clever techniques, watching Alpha Centauri A and B for many hours across a stretch of nights in 2019, gathering as much faint light as it could and carefully subtracting away the interference. The team behind it, including the astronomer Kevin Wagner and his colleagues, published their results in 2021. What they found was not a clear planet, it was a hint. Buried in their data was a faint point of light in a plausible place for a warm planet in the mild zone of Alpha Centauri A. They labelled it a candidate, and they were careful about it. A single faint source in a difficult mid-infrared search can have several explanations. It might be a real planet. It might be a stray artifact of the instrument or the processing. It might be some background object far behind the stars. They could not tell for certain, so they reported it honestly as a possible signal, worth chasing, not yet a discovery. That candidate, sometimes noted in the later work as an earlier source labelled C1, is the quiet seed of our whole story. It said, in effect, there might be something warm sitting out in the habitable zone of the nearest sun-like star. It was not enough to celebrate. It was exactly enough to justify a much harder, much more powerful look. If a ground telescope fighting through the atmosphere could catch even a hint of a warm point of light there, then a cold telescope above the atmosphere with a bigger mirror and a better coronagraph might be able to confirm it or rule it out. This is often how discovery actually moves, not in a single flash, but in a hint that earns a second look, and then a second instrument built to test the first. The NEAR result did not prove a planet. It made the case that Alpha Centauri A was worth the extraordinary effort of a dedicated Webb campaign. It pointed the great new telescope at a specific hopeful spot in the sky. Behind that pointing was a particular community of people, patient and determined, who had been quietly working for years to search the nearest system for another Earth. To understand why Webb was aimed there at all, and why the eventual speck was met with such care, it helps to know who kept watching and why they refused to look away from the star next door. Behind every faint speck in a telescope image stands a group of people who decided it was worth the years of effort to look. The search of Alpha Centauri did not happen by accident. It grew out of a deliberate, funded effort to answer one of the oldest questions we have, whether there is another Earth around the nearest stars, and it drew together astronomers who were willing to attempt something widely considered close to impossible. Much of this effort has been gathered under a set of privately funded programs known as the Breakthrough Initiatives. One arm of that effort, called Breakthrough Watch, is devoted to searching the very nearest stars for small, potentially rocky planets in their mild zones. The NEAR campaign, the ground-based search that produced the first faint candidate, was carried out as part of that push in partnership with the European Southern Observatory. The idea behind Breakthrough Watch is simple to state and hard to do. Focus intense effort on the closest handful of stars, because those are the only places where we could ever hope to study another Earth in real detail, or one day even reach it. That last hope has a companion program worth naming, Breakthrough Starshot, which studies whether tiny probes might one day be sent toward Alpha Centauri, pushed by powerful lasers to a fraction of the speed of light. We will return to that dream near the end of our journey. For now, the point is that the search of the nearest system is not idle curiosity. It is tied to a larger vision of actually knowing, and perhaps someday visiting, the star next door. That vision is what justified pointing the most valuable telescope ever built at such a difficult target. When the time came to attempt the direct search with Webb, the effort was led by a team of experienced astronomers, among them Charles Beichman and Aniket Sanghi, working with colleagues connected to the California Institute of Technology and the Jet Propulsion Laboratory. Aniket Sanghi, then a young researcher, has spoken about being drawn to Alpha Centauri A precisely because it was one of the hardest possible targets, a challenge that others might avoid. That instinct, to go toward the difficult thing rather than around it, runs all through this story. The difficulty was real and specific. Alpha Centauri A is bright, and its companion Alpha Centauri B is bright and close, and both stars move across the sky quickly because the whole system is so near to us. As one of the astronomers put it, these were incredibly challenging observations to make because the stars are bright, close, and moving fast. The operations team had to design a custom observing sequence just for this target, tailored to its particular difficulties, rather than relying on any standard approach. Getting Webb to look cleanly at a spot right beside such a bright, fast-moving star took special planning at every step. So picture the situation as the Webb observations began. Years of patient searching had produced one faint ground-based hint. A community of people had decided the nearest sun-like star was worth an extraordinary effort. The most powerful telescope ever built, with its cold mirror and its Coronagraph, had been aimed at Alpha Centauri A with a custom-made plan. And a small team of astronomers, drawn to the challenge precisely because it was hard, waited to see whether the deep infrared would reveal a warm point of light in the mild zone, or nothing at all. What happened next, in the observations of 2024 and the two that followed, is the heart of our story, and it is where the speck that shouldn't exist finally appears. We will take it slowly and carefully, exactly as the astronomers did. When Webb finally turned toward Alpha Centauri A, the plan behind that single act of looking had been shaped with great care. You cannot simply point the most powerful telescope in space at a bright, fast-moving star and expect a clean image beside it. The star's glare, the nearness of its bright companion, and the speed of the whole system across the sky, all had to be handled deliberately. The observing team designed a sequence built for this one target, unlike the standard routines used on easier stars. Part of the challenge was the Coronagraph itself. To hide Alpha Centauri A behind the mask, the telescope had to be pointed with extraordinary precision, placing the star's light exactly on the small blocking spot and holding it there steadily. A slight drift, and starlight would leak around the edge and flood the very region where a faint planet might sit. With such a bright star, even a small amount of leaked light can bury a planet completely. So the pointing had to be exact, and it had to stay exact, while the telescope tracked a system moving quickly against the background sky. There was also the matter of when to look, because a planet in the mild zone of Alpha Centauri A would move along its orbit over months and years. Its apparent distance from the star changes with time. At some points it would sit farther out, comfortably beyond the mask's hidden circle. At other points it would swing in closer, toward or even behind that circle. The team had to consider where a candidate planet might be at the time of each observation, and choose their moments with that motion in mind. Looking at the wrong time could mean looking when the planet was tucked out of sight. The observations were planned across more than one epoch, meaning more than one separate visit, spaced out in time. This was deliberate and wise. A single image of a faint point of light is always suspect. It could be a real object or a flaw or a stray background source. But if you look more than once and a real planet is there, it should move in a predictable way as it follows its orbit, and it should keep the same brightness and colour. Multiple epochs give you a way to test whether a speck is a genuine orbiting world or just a one-time trick of the light. So the campaign was set up as a series of careful looks, not a single snapshot. The first came in August of 2024. Others would follow in the months after, into 2025. Each would mask the bright star, gather deep infrared light for hours, and then be processed with painstaking care to pull any faint planet out of the residual glare. The team knew that success would not look like an obvious planet leaping out of the image. It would look like a faint point, buried in noise, that had to be coaxed into view and then tested every possible way to see whether it was real. Everything about the plan reflected a hard-won humility. These astronomers understood exactly how easy it is to fool yourself with a faint signal, and how many ways a difficult observation can produce a false one. So they built the campaign to be skeptical of itself, to look more than once, to model the interference carefully, and to demand that any candidate prove itself across the data rather than in a single lucky frame. That care matters because the thing they were about to find would need every bit of it. But before the speck could appear, they had to deal with the second bright star still blazing in the field. The single hardest problem in the whole Webb campaign was not Alpha Centauri A itself, it was Alpha Centauri B. The coronagraph could hide the light of the star it was aimed at, but it could do nothing about the second bright star sitting close by in the sky. Alpha Centauri B kept blazing away from just off to the side, spilling its light across the region, where a faint planet around Alpha Centauri A would have to be found. Masking one star does not help if another one floods the same patch of sky. To understand the trouble, picture the coronagraph doing its job perfectly on Alpha Centauri A, casting the star into shadow. Now imagine, just outside that shadow, a second searchlight shining in from the edge of the frame. Its glow washes across everything, including the exact spot where you're hunting for a faint point of warmth. No amount of masking the first star removes the second star's spilled light. It has to be understood and subtracted carefully after the fact. The team's solution was clever, and it relied on a stand-in. To subtract the unwanted light, you first have to know exactly what that light looks like as it flows through the telescope's optics, how it spreads and ripples and forms its faint patterns. So the astronomers observed a completely different ordinary star chosen for being unremarkable and used it as a model. They watched this reference star both centered on the coronagraph, where it was masked, and shifted off to the side, where it shone unmasked. By seeing how a single known star's light behaved in both positions, they built a detailed picture of how starlight moves through Webb's optics and spreads across the image. With that model in hand, they could return to the Alpha Centauri data and account for the stray light of Alpha Centauri B. Knowing how a star's glow spreads, they could estimate how much of Alpha Centauri B's light was falling on each part of the image and remove it, peeling back the second searchlight's interference to see what lay beneath. It is delicate work. Subtract too little, and the planet stays buried under residual glare. Subtract too much, and you risk erasing a real signal or inventing a false one. The whole result depends on modelling that stray light just right. This is the unglamorous heart of direct imaging, and it deserves to be seen plainly. Finding a planet next to a bright star is only partly about the telescope and the mask. Much of it is about mathematics and modelling, about understanding every source of stray light so precisely that it can be stripped away, leaving only what truly belongs to the sky. The planet, if it is there, does not announce itself. It emerges only after layers of interference have been carefully identified and removed. When the team had done this work on the August 2024 data, subtracting the light of Alpha Centauri A behind the mask and modelling away the spilled glare of Alpha Centauri B, they looked at what remained. In that cleaned image, in the region around Alpha Centauri A, where a warm planet in the mild zone could sit, there was something. A faint point of light, about 10,000 times dimmer than the star it sat beside, glowing in the deep infrared. After all the masking and modelling and subtraction, a speck remained. That speck is what we have been walking toward this whole time. In the cleaned image from August of 2024, after all the careful work of hiding one star and modelling away the other, a single faint point of light remained near Alpha Centauri A. The team gave it a plain label, S1, the kind of neutral name astronomers use for a source they have found but not yet explained. That modest label carried an enormous possibility. S1 sat right where a planet in the mild zone of the nearest sun-like star could be. The speck was faint almost beyond belief. It shone about 10,000 times dimmer than Alpha Centauri A beside it. To pull a point of light that faint out from beside a star that bright, in a crowded system with a second star blazing nearby, is a genuine feat. This is the kind of contrast that had kept the bright pair empty on our maps for so long. And yet, there in the deep infrared, at 15 microns, where a cold but warm enough world would glow, S1 held steady in the data as a real point rather than a smear of leftover noise. What made S1 more than just a hopeful smudge was where it sat, and how it looked. Its position placed it out in the region around Alpha Centauri A, where a temperate planet could orbit, roughly the same band in relative terms, where Earth circles the Sun. Its brightness and colour, its glow in that deep infrared light, matched what astronomers would expect from a large, cool planet warmed to well below freezing. The speck was not just any faint dot. It was a faint dot of the right brightness, in the right place, in the right light. There was one more reason the team took S1 seriously, and it reaches back to the earlier ground-based work. The old NEAR campaign, years before, had reported its own faint candidate near Alpha Centauri A, that earlier source noted as C1. When the astronomers considered whether S1 could be the same object seen again, the pieces were compatible. A source of a similar brightness in a plausible matching position, glimpsed first by a ground telescope and now by Webb. Two independent instruments, years apart, catching a faint point of warmth near the same star. That is exactly the kind of coincidence that turns a shaky hint into something worth real attention. Still, the team was careful, and their care is part of what makes this story trustworthy. A single detection, in a single image, of a source this faint, in observations this difficult, is never enough to declare a planet. Too many things can produce a lone speck. The honest scientific stance was to call S1 a candidate, a promising point of light that might be a world and might not, and then to test it as hard as possible. That is precisely what they set out to do with the other observations in the campaign, the ones taken after August. For a moment, though, sit with what had been glimpsed. A faint warmth, 10,000 times dimmer than the star, in the mild zone of the closest sun-like star to the Sun, matching an earlier hint from a different telescope. If it was real, it would be extraordinary, the closest planet in a habitable zone around a star like our own, caught in its own infrared glow. The team had every reason to hope and every reason to doubt. And then they looked again in the later observations, and the story took its strangest turn. When they went back to that same patch of sky, the speck was not there. The whole point of looking more than once was to test whether S1 was real. A genuine planet caught again in a later image should show itself once more, shifted a little along its orbit but keeping the same brightness and the same colour. So when the team gathered further observations into 2025, they had a clear expectation. If S1 was a world, it should reappear. It did not. In the later looks, the faint point of light was simply absent. The astronomers searched the cleaned images where a planet should have been, given its likely orbit, and found nothing there that matched S1. The speck that had glowed so hopefully in August had, in the follow-up data, vanished. A planet that appears once and then cannot be found again is exactly the kind of result that forces a scientist to be honest about doubt. There is an innocent explanation for a real planet going missing, and it comes straight back to the coronagraph's blind spot. Remember that the mask hides not only the star but a small circle of sky wrapped tight around it, the region inside the inner working angle. A planet catchable when it sits farther out can slip behind that hidden circle as it swings closer to the star along its orbit. The team considered exactly this. If S1 was a real planet on a particular orbit, it might, by the time of the later observations, have moved in too close to the star, vanishing behind the mask rather than out of existence. In that case, the disappearance would not be a mark against the planet. It would be the natural result of an orbiting world moving through the one place the telescope cannot see. But an innocent explanation is not the same as proof, and the team knew it. There is another, harder possibility. A faint speck that appears in one difficult image and never again might not be a planet at all. It could be a chance fluctuation in the noise, a fluke arrangement of leftover light and detector quirks that happen to look like a point source that one time. Difficult observations pushed to their very limit can produce such false points. The honest truth is that a single epoch detection, unrecovered in later looks, sits right on the knife's edge between a real world temporarily hidden and a phantom that was never there. This is the tension at the very centre of our story, and it is why the speck is so aptly described as something that shouldn't be there, in more than one sense. In one sense, a giant planet in this spot challenges what we expected such a system to hold. In another, plainer sense, the speck literally is not there in most of the images. It appeared once, in the deep infrared, 10,000 times dimmer than its star, and then it was gone. The team resisted the pull to overclaim, and that restraint is admirable. They did not announce a confirmed planet. They laid out a candidate, S1, described exactly when it appeared and when it did not, and then did the careful modelling work to ask which explanation the data favoured. Could a real planet, on a plausible orbit, both produce the august detection and be hidden during the later looks? Or was the whole thing more likely a fluctuation? Answering that meant turning from images to orbits and asking whether a single self-consistent world could account for everything that was and was not seen. That is where the analysis turned next. To take S1 seriously, the team had to ask a demanding question. Could a single real planet, moving on one consistent orbit, explain both the speck that appeared in August and its absence in the later observations? If yes, then S1 stayed alive as a candidate. If no consistent orbit could thread that needle, the case would weaken toward S1 being a phantom. This was the work of a companion study to the discovery paper, a detailed modelling of the system, the possible planet, and the search itself. The reasoning runs like this. Suppose there really is a planet in the mild zone of Alpha Centauri A. It follows some orbit, at some distance, tilted at some angle to our view. As it moves, its apparent position beside the star changes. Sometimes it sits far enough out to be seen beyond the mask. Sometimes it swings inward, behind the hidden circle. So the astronomers explored a great range of possible orbits and asked, for each one, a simple thing. Would a planet on this orbit have been visible out beyond the mask in August of 2024? And would that same planet have moved in close, behind the mask, by the times of the later looks? Some orbits pass this test. There are paths a planet could follow that would place it in a catchable spot at the moment of the first observation and then carry it inward into the hidden zone by the time of the follow-up images. On such an orbit, a single real world would produce exactly the pattern seen, one detection, then silence, without ever ceasing to exist. The disappearance becomes not a contradiction, but a prediction. The planet did not vanish, it stepped behind the shield. That is a genuinely encouraging result, and it is worth stating plainly. The modelling showed that the strange behaviour of S1, appearing once and then not again, is consistent with a real planet on a reasonable orbit around Alpha Centauri A. The candidate survived the test. Its disappearance did not rule it out. If anything, it fit a coherent picture in which a warm giant swings through the mild zone, ducking in and out of the region the coronagraph can search. But the same careful work refused to let hope run ahead of evidence. Consistency is not confirmation. Showing that a real planet could produce the observations is not the same as showing that a real planet did. Other explanations still had to be weighed, and as far as possible ruled out. A faint noise fluctuation could also by chance appear once and never again, no orbit required. The modelling narrowed the possibilities and kept the planet alive, but it could not on its own close the case. This is the patient, unglamorous rhythm of real discovery. You find a faint thing. It behaves strangely. You build a model to ask whether a real object could behave that way, and you find that yes, it could, on certain orbits. That keeps the candidate on the table without promoting it to a fact. It also tells you where to look next, because the surviving orbits predict where the planet should be at future times. A confirmed planet would be one caught again, in the place a valid orbit says it should reappear once it swings back out from behind the mask. Before reaching that hope, though, the team had to face the alternatives head-on. If S1 was not a planet on a hidden orbit, what else could a single faint infrared speck near a star turn out to be? The most stubborn of those alternatives sits not beside the star at all, but far, far behind it. When a faint point of light appears near a star in a single image, one alternative haunts every astronomer, and it must be taken seriously. The speck might not be near the star at all. It might be something far in the background, a distant object that happens by pure chance to line up along the same line of sight. The most common culprit is a galaxy, remote and small, glowing faintly in the infrared from immensely far away. This confusion is easy to underestimate until you remember how flat an image is. A telescope records the sky as a two-dimensional picture with no built-in sense of depth. A point of light that sits close beside a star in that picture might truly be a planet orbiting that star only a few light years away, or it might be a galaxy billions of light years beyond, so distant that its light has travelled across most of the age of the universe to reach us, and it just happens to fall in the same spot on the image. In a single frame, the two can look identical. A faint dot is a faint dot. Background galaxies are especially troublesome in the deep infrared, the very light Webb was using. Distant galaxies glow strongly in those wavelengths, and Webb, built to see the faint infrared of the early universe, is exquisitely good at detecting them. So the same power that lets Webb catch a warm planet also fills its images with countless faint, far-off galaxies. Any one of them, landing near Alpha Centauri A by chance, could masquerade as a planet in a single look. Distinguishing a nearby world from a distant galaxy is one of the central difficulties of this kind of search. There is a clean way to tell them apart, and it relies again on motion and time. Alpha Centauri, being so near, moves noticeably across the sky as the years pass, both from its own travel through the galaxy and from the shifting of our viewpoint as the Earth circles the Sun. A real planet orbiting Alpha Centauri A would move along with the star, staying bound to it, and would also trace its own orbital motion around it. A distant background galaxy, by contrast, is effectively fixed. It would not follow the star. Over time, the star and any true companion would drift together, while a background object would be left behind, sliding away in the image as the nearer star moved on. This is why repeated observations across time are so valuable, and why the disappearance of S1 cuts in more than one direction. If S1 had reappeared in the later images in a spot consistent with an orbit bound to Alpha Centauri A, that would have argued strongly for a real planet and against a background galaxy. Its absence, though consistent with a planet hidden behind the mask, does not by itself settle whether the original speck was a bound world or a chance alignment with something far behind. So the background galaxy remains one of the honest alternatives on the table. The Augur speck could have been a warm giant planet in the mild zone. It could also have been a distant galaxy that happened to sit in just the wrong place, mimicking a planet for one image before the star drifted on. The team weighed this possibility carefully, as they had to. It is part of why S1 is called a candidate and not a confirmed world, and it is not even the last of the confounders. Beyond distant galaxies lies a subtler source of false light, one that surrounds the star itself, made of dust. Even setting aside distant galaxies, there is another source of stray light that can confuse a search like this, and it lives right in the system you're studying. It is dust. Not the dust of a dirty room, but fine grains of rock and ice spread thinly through the space around a star, warmed by starlight until they glow faintly in the infrared. Astronomers call this kind of glowing dust, when it lies in the warm inner region of a planetary system, exozodiacal dust. The name carries a small piece of history. In our own solar system, sunlight scattering off fine dust in the plane of the planets produces a faint glow, sometimes visible from dark skies, called the zodiacal light. The same phenomenon around another star is exzodiacal light, the exo meaning outside, beyond our own system. It is the same idea, a haze of tiny particles catching and re-emitting a star's warmth, spread through the region where planets orbit. This dust is a real problem for direct imaging, and in two ways. First, its overall glow adds a soft background of infrared light across the very region where you're hunting for a planet, raising the level of interference you must see through. A thick enough haze can bury a faint planet in its diffuse shine. Second, and more insidiously, dust is not always smooth. It can clump and form bright knots or arcs, and a bright clump of dust seen in a single image can look very much like a point of light. A dust concentration could, in principle, masquerade as a planet, a false speck made not of a world but of glowing grains. So the team studying Alpha Centauri A had to reckon with exozodiacal dust as part of their analysis. They looked at how much such dust the data would allow around the star, and they were able to place limits on it, an upper bound on how much warm dust could be present without having shown up clearly in the observations. Establishing those limits matters for its own sake, because the amount of dust around a star affects how hard it will be to find small planets there in the future. A dusty system is a foggy one to search. A clean system is clearer. For S1 specifically, the dust question folds into the larger uncertainty. A single faint speck might be a planet, or a background galaxy, or a bright clump in a dust cloud. Ruling each of these in or out is exactly the painstaking work that stands between a candidate and a confirmed discovery. The team's careful accounting of the possible dust, and their limits on it, are part of the honest bookkeeping that keeps S1 in the category of promising but unproven. Notice the pattern that has emerged across these chapters. Every step of this search is a fight against things that can imitate a planet. The glare of the target star, the spilled light of its bright companion, distant galaxies lurking behind, glowing dust spread through the system. Each of these can produce light where you're looking, and each must be understood, modelled, and subtracted or bounded before a faint point can be trusted. The speck called S1 had to survive all of them, and the truth is that it survived some tests and remains untested against others. Yet amid all this doubt, there is one detail that pulls the other way, one reason the astronomers leaned toward taking S1 seriously. It is not just that a planet could explain the data, it is that a planet had, in a sense, been expected to be roughly there. Among all the reasons for doubt, one detail gives the candidate a quiet strength, and it is the most persuasive point in its favour. The place where S1 appeared was not a random spot in the image. It was close to where a planet, if one existed, had been expected to be. The speck landed in agreement with a prediction, not in defiance of one. Recall the earlier ground-based hint, the faint candidate from the NEAR campaign, that earlier source noted as C1. From that first glimpse, astronomers had a rough idea of where a possible planet around Alpha Centauri A might sit, and how it might move. When they later considered plausible orbits consistent with that early hint, they could ask where such a planet would be at the time of the Webb observations. The August speck, S1, fell in a position compatible with that expectation. In other words, an earlier independent instrument had pointed to a rough location, and Webb, looking years later, found a faint point of light in a place consistent with a planet on such an orbit. This is a very different situation from finding a lone speck with no prior reason to expect anything there. A random faint dot, appearing once, is easy to dismiss as noise or a background object. But a faint dot that appears where a separate earlier observation suggested a planet might be, and at a brightness matching what such a planet should have, is a coincidence that grows harder to wave away. Two difficult independent measurements, made years apart with different telescopes, pointing to a warm object in compatible places, begin to reinforce each other. It is worth being precise about how much weight this carries, because it is easy to overstate. The agreement is not perfect proof. Both the earlier hint and the Webb speck are faint, hard-won detections, each with its own uncertainties. The predicted region for a planet was broad, not a pinpoint, so a chance object could still land within it. And the later disappearance of S1 means the reinforcement stops at a single Webb detection, rather than a clean, repeated track across many images. The prediction fitting is a genuine point in favour of a real planet, not a closed argument. Still, this is how confidence is built in astronomy, brick by careful brick. A hint from one telescope, a detection from another in a compatible place, at a compatible brightness. Modelling that shows a single real planet could produce both, on an orbit that would also explain the later absence. None of these alone is decisive. Together they form a coherent picture in which a warm giant planet moves through the mild zone of Alpha Centauri A, glimpsed twice by two instruments and hidden the rest of the time behind the coronagraph's mask or in the noise. It is not certainty. It is a hypothesis that keeps surviving its tests. That is why the team, for all their careful hedging, treated S1 as a candidate worth announcing and pursuing, rather than a curiosity to be set aside. The weight of the evidence, the matching brightness, the compatible position, the consistency with an earlier hint, the orbits that could tie it all together, tilted towards something real being there, even as honesty demanded the label candidate remain. And so we arrive at the question that makes this whole search matter. Suppose for a moment that S1 is real. Suppose there truly is a giant planet in the mild zone of the nearest sun-like star. What would that actually mean? And why would it be worth all this effort? The answer reaches beyond one faint speck, into what we understand about planets, and about our place among the nearest stars. Suppose S1 is real. Suppose that faint speck in the August image truly is a planet orbiting Alpha Centauri A, and that the later confirmation still to come will bear it out. What would we actually have found? The answer is worth savouring, because it would be a genuine milestone in the search for other worlds. First, it would be close. Alpha Centauri A sits just over 4 light-years away, at the very edge of our stellar neighbourhood, the nearest sun-like star there is. A confirmed planet there would be, by a wide margin, the closest planet ever directly imaged in the mild zone of a star like our own. Not detected by a wobble or a shadow, but seen, caught in its own infrared glow. The closest possible example of a planet in the temperate band around a true solar twin, near enough to study as no other such world could be. Second, it would be a giant. The brightness of S1 suggests something large, a gas giant, likely between the sizes of Saturn and Jupiter. That is not a small rocky world like Earth. It is a big gassy planet, more akin to our own outer giants than to our home. Warmed to well below freezing, around 50 degrees below zero on the Celsius scale, it would be a cold giant sitting where a temperate planet could be. A strange and interesting combination. Not a place for life on the planet itself, but a major world in exactly the region we most want to understand. Here is the deeper significance. Such a planet would sit in the habitable zone of a sun-like star, the very band where, around our own sun, Earth resides. A large planet there tells you that this system managed to build and hold a substantial world in its temperate region, despite the disruptive pull of the second bright star. That alone would teach us something real about how planets form and survive in double star systems, which are common in the galaxy. It would say that even a stirred-up binary can keep a big planet in its mild zone, which is not something we could take for granted. There is also what a giant implies about its surroundings. A large planet shapes the space around it with its gravity, herding smaller bodies, clearing or stirring regions of the system. If a gas giant sits in the mild zone of Alpha Centauri A, it would strongly influence any smaller, rocky worlds that might also be there, nudging their orbits, perhaps shepherding them, or perhaps unsettling them. Finding the giant would immediately raise the question of what else the system holds and how the giant's presence has shaped it, and a confirmed planet would become a prize target for the future. Being so near and, if real, large enough to catch, it would be one of the best possible objects for the next generation of telescopes to study in detail. Astronomers could spread its light into a spectrum and begin to read the gases in its atmosphere, learning what a cold giant around a sun-like star is actually made of, in a way possible nowhere else because nowhere else is this close. So the stakes behind that faint speck are high, not because a cold gas giant is itself a likely home for life, but because it would be the nearest window we have ever had into a planetary system around a star like our own. If S1 is real, it is a doorway. And even a cold giant carries one more possibility for gentleness, not on the planet itself, but circling it in the worlds a giant so often keeps. A cold gas giant is not, in itself, a place we would look for life. It has no solid surface to stand on, and its outer layers are frigid and deep, but a giant planet rarely travels alone. In our own solar system, the great planets are each surrounded by families of moons, some of them worlds in their own right. So if S1 is a real gas giant in the mild zone of Alpha Centauri A, it is natural to wonder about the moons it might hold, and whether any of them could be gentle. The idea is not idle. Look at our own giants. Jupiter and Saturn each carry dozens of moons, and among them are places that have become central to the search for life beyond Earth. Some of these moons are thought to hide oceans of liquid water beneath icy shells, kept warm not by sunlight, but by the constant flexing that a giant planet's gravity works on them. The giant squeezes and stretches its moon as the moon orbits, and that flexing generates heat deep inside, enough, in some cases, to melt a hidden sea. A moon far from its star can still be warm within, warmed by its planet rather than its sun. Now place a giant planet in the mild zone of a sun-like star, where starlight is also gentle and temperate. A large moon around such a giant would have two sources of possible warmth: the mild light of the nearby star and the tidal flexing from its planet. In principle, that combination could make for a moon with liquid water, a small world riding around a giant, warmed from without and within. This is why, when astronomers imagine a cold giant sitting in a habitable zone, they do not simply set aside the question of a life, they turn instead to its possible moons. Honesty requires holding this lightly, because it is speculation resting on speculation. We do not yet know that S1 is a real planet. If it is real, we do not know that it has large moons, and we cannot currently detect moons around a planet 4 light-years away. The chain of ifs is long. A moon warm enough and stable enough to hold liquid water around a giant that may or may not exist is a possibility to note, not a discovery to claim. It belongs in the realm of what could be, not what is. Yet the possibility is real enough to keep in view, because it changes how we think about cold giants in mild zones. A planet like S1 would not be a dead end in the search for gentle places. It would be a potential host, a giant that might carry warm moons around a sun-like star in the nearest system to our own. That is a tantalizing thought, and it is one reason a cold gas giant in this particular spot is worth so much attention. For now, the moons remain imagined, a soft possibility hovering around an unconfirmed planet. What is not imagined is the effort now underway to settle the harder question first, whether S1 is truly there at all. A candidate that appears once and hides the rest of the time cannot stay a candidate forever. Either future observations will catch it again, in the place a valid orbit predicts and confirm a real world, or they will fail to find it, and the speck will fade back into the noise from which it came. How astronomers plan to force that resolution is the next part of the story. A candidate cannot remain a candidate forever. Either S1 is a real planet, in which case it should be catchable again when it swings back out from behind the mask, into the region a valid orbit predicts, or it is not, in which case repeated careful looks will keep coming up empty until the case quietly collapses. The way forward is more observations, from more instruments, and several are on the horizon. The most direct path is simply to keep watching with Webb itself. The modelling that kept S1 alive also predicts where a real planet should be at future times. As the planet, if it exists, continues along its orbit, it should emerge again from behind the coronagraph's hidden circle into a spot where Webb can see it. Timed correctly, future Webb observations could catch S1 a second time, in a position consistent with a bound orbit around Alpha Centauri A. That would transform it from a one-time speck into a tracked moving world, and would rule out both a background galaxy and a chance fluctuation. A single clean recovery, in the right place, would change everything. Beyond Webb, a new space telescope is on its way that is especially suited to this kind of work. It is called the Nancy Grace Roman Space Telescope, and it carries an advanced coronagraph built to demonstrate the very techniques needed to image planets near bright stars. Roman's mirror is smaller than Webb's, but its coronagraph is a technology testbed designed to push the art of suppressing starlight to new levels. Aimed at the nearest systems, including Alpha Centauri, Roman could add independent observations that either support or challenge the Webb detection, using a different instrument with its own strengths. Then there are the giant telescopes rising on the ground, a new generation of enormous observatories with mirrors far larger than anything built before is under construction. Their great size gives them extraordinarily sharp vision, the ability to separate a planet from its star at very small angles, and to gather enough light to study faint worlds in detail. Once operating, these telescopes could turn toward Alpha Centauri and search for S1 and any companions, potentially confirming a planet and even beginning to probe its atmosphere. The combination of a nearby target and a huge telescope is exactly what direct imaging most wants. The picture, then, is not one telescope alone but a coming convergence. Webb, returning to the target to catch the planet emerging from behind the mask. Roman, adding a space-based second opinion with a purpose-built coronagraph, and the giant ground telescopes, bringing their vast light gathering and sharpness to bear. Between them, Over the next years, the question of S1 should move from open to settled. A real planet cannot hide from all of them forever. A phantom cannot fool all of them at once. This is a hopeful place to stand. The speck is uncertain now, but its uncertainty has an expiration date. Unlike some cosmic mysteries that may stay out of reach for generations, this one sits at the nearest system, the easiest possible target, squarely within the reach of instruments already flying or being built. We do not have to wonder forever. We have only to keep looking at the right times with the right eyes, and behind all this patient watching lies a bolder dream, older than any of these telescopes, the wish not merely to see the nearest system but somehow to reach it. That dream, too, has quietly become a subject of serious study. Behind every effort to study Alpha Centauri lies a wish that is older and bolder than any telescope, the wish to actually go there. It sounds like pure fantasy, and by the standards of our current rockets it is. But there is a serious, carefully studied proposal that treats the journey not as fiction, but as an engineering problem, and it is worth knowing because it reveals just how much the nearest system tugs at us. The proposal is called Breakthrough Starshot, part of the same family of privately funded efforts as the searches we have followed. Its central idea sidesteps the crushing problem of interstellar distance in a clever way. Instead of building a massive ship carrying fuel for a decades-long burn, which is beyond anything we can do, it imagines sending something almost weightless. Picture a tiny spacecraft, no heavier than a small chip, attached to a thin, wide sail. The spacecraft carries little more than a camera, some sensors, and a way to send signals home. Everything about it is made as light as possible. The trick is how you push it. A sail catches light and feels a gentle pressure from it, the faint push of photons striking its surface. On Earth that push is far too weak to notice, but aim an immensely powerful array of lasers at a light sail in space, concentrating enormous energy onto it for a few minutes, and that gentle pressure becomes a hard shove. The idea is to drive the tiny sail up to a large fraction of the speed of light in that brief burst of laser light, and then let it coast, unpowered, across the Gulf to Alpha Centauri. At such a speed, the journey shrinks from tens of thousands of years to something like a couple of decades. A probe launched in a person's youth could reach the nearest star within their lifetime, flash through the Alpha Centauri system in a matter of hours, snapping images and taking measurements, and beam the data back across the 4 light-year gap. The data would then take a little over 4 years to arrive, crawling home at the speed of light long after the probe itself had swept past. The wait would be long, but a first close look at another star system would finally be within a single human span. The difficulties are staggering, and honesty demands naming them. Building lasers powerful enough, sails that can survive the strain without tearing or melting, electronics tiny enough yet tough enough to endure the journey and the radiation, and a way to steer and communicate across such distances, all remain far beyond what we can do today. Breakthrough Starshot is a study of whether such a thing might one day be possible, not a mission on a launch pad. It may take generations of advances, or it may prove impractical. But it is being taken seriously, examined by real engineers and scientists precisely because the target is so near. And that is the point worth holding. Every planet found around Proxima, every faint speck sought near Alpha Centauri A, feeds the same quiet hope. If we ever do send something across, we would dearly want to know what waits on the other side. A confirmed planet, a giant with possible moons, a temperate world. Any of these would give a future probe a destination, a specific thing to fly toward and photograph. The search and the dream of the journey are bound together. To know the nearest system is the first step toward perhaps one day reaching it. Step back now from the single speck and consider what this whole search has been quietly teaching us, whether or not S1 turns out to be real. The lesson is about how planets form and where they can survive, and it gently unsettles some of what we thought we knew. For a long time, the expectation was that a system like Alpha Centauri, with 2 bright stars orbiting close together, would be a hard place to build large planets. The gravity of a stellar companion disturbs the disk of gas and dust from which planets grow, truncating it and stirring it, making it difficult, so the model suggested to assemble a big planet in the mild zone of either star. Small rocky worlds might manage, but a true giant there seemed unlikely. That expectation is exactly why a candidate giant, if confirmed, would be described as something that shouldn't be there. It sits against the grain of what we predicted. Whenever nature places something where our models didn't expect it, that is not a failure to be embarrassed about. It is an invitation to learn. If a giant planet really does orbit in the habitable zone of Alpha Centauri A, then our understanding of how planets form in double-star systems is incomplete and needs revising to allow for it. Binary systems are extremely common in the galaxy, so knowing whether they can hold large planets in their temperate zones matters far beyond this one case. A single confirmed world at the nearest system could reshape our sense of how many double stars across the galaxy might carry substantial planets. Even the uncertainty itself teaches something. Notice how much effort it took to find, and still not confirm, a giant planet at the very nearest sun-like star, the easiest imaginable target. The glare, the second star, the background galaxies, the dust, the coronagraph's blind spot, all of it conspired to make even this closest search agonizingly hard. That difficulty is a lesson in humility. If finding a large planet is this hard at 4 light years, we should be modest about how much we can currently see around more distant stars, and patient about how slowly the picture will fill in. There is a broader shift here too, from indirect to direct. For decades, nearly everything we knew about planets around other stars came from indirect signs, the wobbles and shadows. The effort at Alpha Centauri A represents the harder, richer path of catching a planet's own light. That path is only beginning, and it is where the future lies, because only direct light lets us truly study a planet's atmosphere and character. The struggle to image S1, successful or not, is a rehearsal for a coming era in which we hope to see, and not merely infer, the worlds around the nearest stars. So the search has value regardless of how S1 resolves. If it is confirmed, we learn that giants can form and survive in the temperate zones of binary stars, and we gain the nearest imaged planet around a sun-like star. If it fades into noise, we learn how the closest system tricked us, and we sharpen the tools and the caution we will need for every search to come. Either way, we come out knowing more than we did, both about the star next door and about the limits of our own seeing. And that brings us back at the end to where we began, to a faint point of light and the quiet wonder it stirred on a dark night. We began with the nearest light in the sky, the star system whose glow reaches us across a little more than 4 years of empty space, and we can end there too, with everything we have learned settling gently into place. The journey has been long, but the shape of it is simple. We looked at the closest stars and we found them full of worlds and mysteries. Remember the small red ember, Proxima Centauri, faint enough to hide from the naked eye yet close enough to be our nearest star. Around it we found 3 planets, in one form or another, red from the star's tiny swaying motion. A rocky world in the mild zone, a distant disputed super-Earth in the cold, a featherweight so light that finding it meant measuring a star's crawl speed sway across 4 light years. For a dim star most people cannot even see, Proxima proved astonishingly rich. And remember the bright pair beside it, Alpha Centauri A and B, so hard to search that they stayed blank on our maps for years. Toward the brighter of them, a sun much like our own, we aimed the most powerful telescope ever placed in space, hid the star behind a mask, modelled away the glare of its companion, and looked into the deep infrared for the heat of a hidden world. In one image, from August of 2024, a faint point of warmth appeared, 10,000 times dimmer than the star, exactly where a planet could be. And then, in the later looks, it was gone. That speck, called S1, is where all our care converged. It might be a giant planet in the mild zone of the nearest sun-like star, hidden in the follow-up images behind the coronagraph's shield. It might be a distant galaxy, or a clump of glowing dust, or a flicker of noise that only looked like a world for a single frame. The evidence leans one way and then the other. A matching hint from an earlier telescope, and orbits that could explain both its appearance and its absence, argue for something real. Its silence in most of the images, and all the things that can imitate a planet, keep the case open. So it remains, honestly, a candidate. There is a particular kind of wonder in that unfinished state. We are not looking at a settled fact, but at a question caught in the act of being answered, at the nearest possible place, with the finest tools we have ever built. And unlike so many cosmic mysteries, this one will not stay unresolved forever. Webb will look again, time to catch the speck emerging from behind its mask. New telescopes will turn the same way. Within a few years, S1 will step into the light and become a confirmed world, or fade back into the dark from which it came. Whichever way it goes, sit for a moment with the plain fact that started us off. The nearest star's light reaches us in the span of a childhood, and around those nearest stars worlds are turning. Some we have found. One we are still not sure of. All of them are close, in the vast scale of things, close enough to study, close enough to dream of reaching. The next time you picture that bright point low in the southern sky, you can hold in your mind a whole system of worlds and one faint speck of warmth, waiting quietly to tell us what it is.